Depending on the resource you're using, either a textbook, handbook, or an instructional website, or even an engineer that works with gears, you'll find a different categorization for the available types of gears. We will end up using a 4-main category system with spur, helical, bevel, and worm gears, but we'll talk about those later. Today, we will look at the simple spur gears to identify some of the vocabulary and nomenclature we will use for their geometry, so that we can cover the kinematic relationships, force, torque, and power transmission, and eventually stresses and strengths that will allow us to calculate the overall reliability of gear systems. And of course, gear systems is not just the analysis of the gears themselves. This will include the shafts we studied in earlier videos, as the different gear types introduce all the external forces that affect the shaft design we covered, and all of the fatigue concepts we've been applying to the different machinery components. After this, we will transition to bearings, which of course is related to the shafts, and that includes bearings design and selection. We've talked about pitch for other components, like screws and springs, and in every case, the pitch refers to a distance between repeating elements, like threads in the case of screws, or coils in the case of springs. If we look at a couple of teeth of a spur gear, where would you define the pitch, or the distance between one tooth and the next? Would it be at the base or at the top? Would it be a straight line distance, or over the circumference of a circle? It makes sense that it is defined as an arc, a curved distance along the circumference of a circle, but where would that circle be located? We define circular pitch as the arc distance from one tooth to the next, which means is not the distance on a straight line, but a distance along the circumference of a circle, in this case, along the pitch circle. The pitch circle is what separates the dedendum from the addendum. When one tooth of a spur gear is in contact with the tooth of another gear, the point of contact will slightly shift as both of them are rotating. The average location of the point of contact occurs exactly at the pitch circle. Alternatively, you could just picture that the pitch circle of one gear will intersect with the pitch circle of the maiden gear. This pitch circle has a diameter that we will call the pitch diameter. Remember when you talked about the radius of a gear when working on simple angular velocity and torque topics in physics? Or the radius of a gear in a simple gear setup during your mechanics of materials torsion examples? What radius were you using then? Was it the distance from the center to the base of the gear? From the center to the top of the teeth? Even if you didn't know it then, it was a radius equivalent to the pitch diameter divided by 2, or just the pitch radius. So every time we refer to the diameter of a gear to talk about the relationship between number of teeth, angular velocity, or torque, we will be using this pitch diameter. The circular pitch, that distance between one tooth and the next, will for this reason be equal to the circumference divided by the number of teeth. Even though the circular pitch is what defines that distance, which makes total sense for a pitch, we usually use the module for metric units, which is the same as the circular pitch without the pi, and the diametral pitch for English units, which for whatever reason is the reciprocal of that. The units of the module would be millimeter per teeth, and the units of the diametral pitch are teeth per inch. The involute profile refers to this very precise shape the tooth has. This shape would guarantee that the point of contact between two teeth, one from each gear of gears in contact, occurs where the two surfaces are tangent to each other. The reason I say would guarantee instead of stating it as a fact is that this only happens for perfectly formed, perfectly smooth, and infinitely rigid teeth, which of course is not the case. Regardless of the imprecisions, the fact that the point of contact occurs where the two surfaces are tangent to each other means that the forces at any moment during contact are pointing in one and only one direction. This line is known as the line of action, and what's important about it is that the angle between it and the tangent line to where the pitch circles meet is called the pressure angle phi. This angle, which used to be 14.5 degrees and is more commonly 20 degrees now, but can take other values, will be very important when we talk about forces and force components, one of which will transfer the torque from one gear to the other, and one of which will cause that bending moment on the shaft that we mentioned before. But more about that in a later video. Now, we're gonna develop 3 separate relationships from 3 distinct conceptual bases. When the gears are designed and mated so that they produce a constant angular velocity during service, which means neither of them will stutter or stop while the other one is still rotating, we say the gears have conjugate action. For the gears to mate properly, the circular pitch, that distance between one tooth and the next, has to be the same for both gears, otherwise that teeth distance would not match. Knowing that the module, diametral pitch, and circular pitch are all equivalent, let's use the diametral pitch to say that P1 has to be equal to P2 for proper mating. If this is true, then the ratio between number of teeth has to be equal to the ratio between the diameter of the gears. And remember that we will always use the pitch diameter as the standard diameter for gears. The second relationship comes from the fact that you don't want the gears to slip. Slipping would introduce friction, which would not only cause the gears to deteriorate over time, but it would mean that the efficiency of the transmitted torque is drastically reduced. Without gears slipping, we have that the arcs from each gear after a specific amount of time are the same, which means that the linear velocity at the pitch circle is the same. From basic physics, we know that the linear velocity is equal to the angular velocity times the radius, and therefore the radii ratio has to be the reciprocal of the angular velocity ratio. Since we usually use the diameter and not the radius, and since we usually talk about revolutions per minute instead of angular velocity, we can multiply by 2 on the numerator and denominator of the left-hand side and divide by 2 pi on the numerator and denominator of the right-hand side. The left hand would be the ratio between gear diameters, and the right-hand side would be the number of revolutions per minute, since there are 2 pi radians per revolution to find omega, the angular velocity. Finally, if we assume that there is no power loss when transmitting torque from one gear to the next, and we'll fix this in a minute with the efficiency concept, then the power in gear 1 is equal to the power of gear 2. Again, from basic physics, power is angular velocity times torque. Dividing by 2 pi and multiplying by 60 on both sides, and I do include the 60 now because power in watts would necessitate an angular velocity in radians per second, not minute, we get RPM times torque, which results in a relation between revs per minute and torques. If we put all of these together, we find that with only one of the ratios, we can find the other three. If there is a loss in power, we introduce the efficiency eta into the last relationship, a fraction between 0 and 1, but we'll talk more about that later. In a 4-gear system that transmits power from shaft A to shaft C without any losses, gear 2 has 40 teeth, gears 3 and 5 are the same gear with 10 teeth and a module of 0.5 millimeters per tooth, and gear 4 has a pitch diameter of 15 millimeters. If shaft A is rotating at 200 revs per minute, what is the input and output torque and the output revs per minute if the power going in is 50 kilowatts? The first one of these questions is almost not related to what we learned today. Maybe it's related to what we reviewed today from physics. If power is equal to the torque times the angular velocity, and the angular velocity is 2 pi over 60 times the revolutions per minute, then the torque is equal to power times 60 over 2 pi n. With 50,000 watts and 200 revolutions per minute, the torque would be 2.39 kilonewton meter. To find the revolutions per minute of shaft C, which is the same as the revolutions per minute of gear 5, I'm gonna need to know the revolutions per minute of gear 4, 3, and 2, and use the relationships we came up with today. I know gear 2 rotates at the same angular velocity as shaft A, and since I know the number of teeth of gear 2 and gear 3, I can use the relationship between revs per minute and number of teeth to find that gear 3 rotates at 800 revs per minute. Gear 3 and gear 4 are on the same shaft, shaft B, and therefore rotating at the same speed. To find the revs per minute of gear 5, I either need the relationship between the number of teeth or the pitch diameter between gears 5 and 4. And since I have the module of gear 5, which is the relationship between the number of teeth and the pitch diameter, I can find that the pitch diameter of gear 5 is 5 millimeters. Since I now have the diameters of gears 4 and 5, I would use the relationship between diameters and revs per minute for gears 4 and 5. From this, I find that the revs per minute of gear 5 is 2400 RPM, which is the same speed as the rotation of shaft C. Finally, to calculate the output torque, I could either repeat this procedure I just did and use relationships that allow me to calculate the torque instead of the revs per minute, or I can use the given power and the revs per minute I found for shaft C to find that torque. If the problem didn't ask for the output speed, but it did ask for the output torque only, I would probably use the relationships from today, instead of using those to calculate a speed that wasn't part of the questions, to then calculate the torque with the power and that speed. As you can see from this gear system, the torque coming in is 12 times the torque coming out, but the output speed is also 12 times higher than the speed I'm giving the system. There are many reasons where you would want to gain velocity even though you lose torque, like for example the higher gears in the transmission of your car, but also you can lose some speed to gain torque, like for example the power screws we studied before. If you want to check out other problems where we make use of these relationships we derived today, make sure to check out the links below. In the next video, we'll take a look at gear trains, somewhat related to what we did today with the example, and a specific case of that, the planetary gears, which will allow us to understand the rotation of the gears and the direction of that rotation. Thanks for watching.